Let me welcome all of you to this, the first of our events of the year 2021. We've had two web presentations already earlier in this season. But this evening, we're very pleased to welcome from Imperial College London, Professor James Durrant. He's in fact a physicist originally, who then studied biochemistry and now works in the chemistry department, which also calls itself the Molecular Sciences Research Hub and Centre for Processable Electronics at Imperial College London, in the campus, which is now at White City, which I think is just across the motorway from the other campus at Hammersmith, where we also have some contacts. After doing these brief introductions, I should add that in addition to his position as a professor in Imperial, he's also got a position as in the chemical engineering department at the University of Swansea. He's going to talk to us this evening about the solar-driven synthesis of sustainable fuels, where photochemistry meets catalysis. I suppose as a carping biochemist, I might say that photochemistry is frequently catalytic as well, but never mind. Please, James, we're looking forward to your talk. Over to you.
Thank you very much for that kind introduction, and it's a real pleasure to be able to join you this evening. Thank you very much for taking the time out of your evenings to come and hear me talk. I hope I can say a few interesting things. Can you see my slides okay? Fantastic. So, indeed, I'm going to be talking about the challenge of what is often called artificial photosynthesis. So it's the challenge of harnessing sunlight to make fuel. And this, of course, is something which aligns very closely with biological photosynthesis. And it's the idea of either splitting water to make oxygen and hydrogen, or going on and producing things like CO2 to hydrocarbon fuel. And I'll be talking, first of all, about why this challenge is interesting and where chemistry can play a role in driving these reactions. And then I'll talk a little bit about my own research, and particularly around some of the photochemistry of generating excitations and using those to drive these reactions. And then I'll talk a little bit about catalysis and the kinetics of catalysis. So that's the summary of what I'll talk about in introduction, and then I'll talk about photochemistry, and then I'll talk about directly the catalysis. I for my life, have worked on trying to understand new materials which may be useful for harnessing sunlight. My PhD was on plants, as it was kindly mentioned in the introduction, trying to understand the primary reactions in the photosystem to reaction sensor. And then most of my research career has been working on solar cells, how we can harness sunlight to make electricity. But over the last 10 years or so, I've kind of gone full circle and have now increasingly focused on the challenge of what is called artificial photosynthesis. So using sunlight to drive reactions which can store energy in chemical bonds. I'm not going to motivate why solar energy is interesting. I think we all understand now that we need to move away from fossil fuels, and that globally we need to shift towards renewable power sources. And of course, sunlight is the most ubiquitous of renewable power sources on our planet. Of course, there are many others, but in terms of scalability, sunlight is the kind of a prima donna in the sense that we have so much of it globally. It's not so easy to capture it and use it efficiently and cheaply. The motivation for solar to fuels rather than solar cells is illustrated here. There already is a drive towards photovoltaics, and of course the cost of solar cells has come down dramatically in the last 10 years or so. And so we already have pathways to reduce the dependence of our electrical power generation on fossil fuels, and even in the UK now, we're increasingly shifting to wind and solar. But the challenge of how we decarbonize fuel and decarbonize heat and decarbonize chemicals remains significant. And so this talk is very much about how we can start to think about and move towards a more sustainable fuel and chemicals. There are other aspects to that. One of the challenges, of course, is that sunlight is intermittent, and that the solar cells turn off when the sun goes down. And increasingly, there's a challenge of storage. There's also the challenge of can we talk a lot about CCS, carbon capture and storage. I'm personally more interested in carbon capture and utilization. Can we use CO2 as a chemical feedstock? And if we're going to do that, where does the energy come from? At the bottom, there's two illustrations of this concept, the concept of, for example, green hydrogen. The UK is now getting very excited about hydrogen. Most of our hydrogen is brown hydrogen from fossil fuels. The government's moving towards blue hydrogen, where they make the hydrogen from fossil fuels but store the CO2. I'm much more interested in green hydrogen, where we make the hydrogen from water using renewable power or renewable energy. We also have the idea of liquid sunshine, which is the idea that I believe both Belgium and the UK will be significant energy importers. And going forward to the future, we need to think about how we are going to import sustainable power. And one of the easiest ways to do that is to imagine that we could synthesize a fuel in a region of the world with large amounts of sunlight, turn that fuel, synthesize hydrocarbons, and then transport those hydrocarbons to Belgium or to the UK as a liquid fuel, for example, in this case, as methanol. And so this would be the idea of using the existing infrastructure we have for moving hydrocarbons around the world. But now we wouldn't get the hydrocarbon out of the ground. The hydrocarbons would be synthesized from CO2 taken from the atmosphere using renewable power. And these are concepts which I think are capturing people's imagination and excitement. But these are also not new concepts. The idea that we can split water to make a fuel is something that Jules Verne was even expounding 150 years ago. And I think it is very prescient that he was already aware of the idea that we can use water, at least if we can split it into hydrogen and oxygen, as a source of energy. And indeed, people more recently have been getting excited. So the quote at the bottom is a quote from Barack Obama some 10 years ago around an initiative called the Joint Center for Artificial Photosynthesis, set up at California to harness sunlight to split water and to reduce CO2. Of course, over the last few years, we haven't heard so much about this from the last president of the United States. So I'm hoping that Joe Biden might get a little more excited going forwards. And of course, a lot of the motivations here are the idea that we're already interested in storing energy in batteries. And there's lots of excitement around batteries and battery-powered cars and all this. But batteries are wonderful, but they have limitations. Their energy density is far lower than storing energy in a hydrocarbon fuel. And also, of course, they're less scalable. If you want to store more energy in a battery, you have to build more batteries. If you want to store more energy in ethanol, you just have to build a larger tank. And that scalability, I think, is critical. And of course, this is all around trying to develop circular economies, in this case, circular economies in carbon dioxide and carbon cycles. People are starting to think about how, if we can sustainably synthesize fuels from renewable power, how that would fit in to energy systems. And you can see one illustration here of how you could imagine systems which either use photoelectrochemistry or electrochemistry to convert simple feedstocks such as water, CO2 and nitrogen into more useful chemicals using renewable power. Indeed, the RSC was one of the first organizations, at least in Europe, thinking about the challenge of solar to fuels, and wrote a rather lovely report some 10 years ago on the challenge of artificial photosynthesis. When we think about how you can use sunlight or indeed other sources of renewable power to synthesize green hydrogen or chemicals or hydrocarbon-based fuels, are you able to see my cursor? Is that okay? Just checking it. That's okay.
Yeah, that's fine.
Yep. Then there are many pathways. We are already able to take sunlight to make electrons, to use those electrons to split water into hydrogen and oxygen, and use the hydrogen to reduce CO2 to a carbon-based fuel. So that's a pathway which exists. Currently, it doesn't compete financially with taking fossil fuels out of the ground. And so, of course, the challenge is making this carbon, these pathways cheaper. And one of the ways to do that is make the solar cells cheaper, the electrolyzers cheaper, and work out how we can reduce CO2 cheaper. Other ways are imagining ways to combine some of the steps. And so, for example, using sunlight directly to split water, or to achieve the electrochemical reduction of CO2. These are now very active areas of research. There are many organizations globally and locally which are driving the concept of sunlight to fuel. In the UK, we have a Solar Fuels Network. In the EU, we have the initiative Sunergy, and Mission Innovation, which will be feeding into the COP26 discussions later this year, has its own Mission Innovation Challenge on converting sunlight. So these are areas where there is now very active research. And much of the research involves chemistry because, of course, the overriding feature of all of these pathways, apart from the photovoltaic pathway here, is catalysis, because we're dealing with difficult chemical transformations and understanding the catalysis and typically electrocatalysis. This is thermocatalysis for dark chemical reduction of CO2, but the electro or photoelectrocatalysis is a major area where chemistry is very exciting and inputting. I'm going to focus in terms of my research, in terms of this talk.
Professor Durrant, switch on your microphone, please.
Sorry. How long was that muted? Did you miss much?
10 seconds.
So I'm going to be focusing on the challenge of the photolysis and the electrolysis of water. But in general, you can see that in almost all of these steps, apart from the photovoltaics, catalysis and therefore chemistry is key. When we think about how you might split water with sunlight, then there are almost, if this is an area where the demonstrations of technology are relatively limited, and there are almost as many concepts of devices and materials as there are researchers working in the field. It's an area of lots of excitement and rather less structure and organization. There are three classical ways you can imagine taking sunlight to split water. One is to take a suspension of some sort of photocatalyst, shine light on it, generate electrons and holes, and these electrons and holes can then drive the reduction and oxidative chemistry.
Sorry, Professor, once again.
Reactions in electrodes, and so this is an example. We have a photoelectrode doing water oxidation.
Professor Durrant, can you share again your PowerPoint presentation, please?
How long did that last?
Okay.
In about 10 seconds.
Okay.
Yeah, what's happening?
Yeah.
Thank you. That's great.
Okay.
Yeah.
So there are three different examples here of systems which you could imagine which can split water. You can imagine particle suspensions where you shine light on a particle, you generate electrons and holes, and these can reduce protons to hydrogen and oxidize water to oxygen. You can separate the oxidation and reduction reactions in two electrodes. This has the advantage that you can apply an extra voltage if it doesn't work very well. Or you can imagine coupling photovoltaics to catalysts. And so you have a solar cell generating electrons and holes, and you apply catalysts either directly to the solar cell or separately to drive the chemistry. And then you can imagine many different examples of materials which can go into these components. Many of these are inorganic. Hematite is one of my favorites because it's so remarkably stable. But of course, hematite is so essentially, in this case, nanostructured rust is a material which is stable and cheap and coloured. It's brown. It's also not a very good semiconductor, and therefore trying to understand the function of hematite is certainly interesting. You can imagine carbon-based systems. These are carbon nitrides, which can absorb sunlight and drive the same sort of chemistry. There are many, many examples of materials which can go into these sorts of devices. And then we have to think about the catalysis. And very often this catalysis is inorganic, heterogeneous catalysis, but increasingly there's interest in molecular catalysis. You can think about the same sort of concepts, not for water splitting, but in this case, for CO2 reduction. Again, you can have particle suspensions, and so this is an example where if you put silver nanoparticles on the surface of titania, it turns out, for reasons we don't understand, they catalyze the reduction of CO2 to methane. You can put molecular catalysts absorbed in titania on top of, in this case, an amorphous silicon electrode to drive the reduction of CO2 to syngas. Or you can imagine coupling solar cells to electrolyzers, which in this case are oxidizing water, but not reducing protons, but rather reducing CO2 to hydrocarbons. Again, of course, the challenge is the catalyst as well as the light absorbers. One of the biggest excitements is the idea that nanostructured copper turns out to be remarkably effective as an electrocatalyst for CO2 reduction. But equally, there's a challenge here about specificity. There's so many products you can have from CO2 reduction. Molecular catalysts have some advantage in terms of specificity. I did my PhD on plants, on photosynthesis. And so when I've been studying how to harness sunlight to achieve useful chemistry, photosynthesis has been my inspiration. You can see an illustration here of a photosynthetic reaction center, the PS2 reaction center in higher plants, which uses sunlight to drive the oxidation of water to release all the molecular oxygen which you breathe in our atmosphere. And of course, plants often get a bad press in terms of their ability to store energy, in the sense that the efficiency of a plant of storing sunlight in biomass is relatively low compared to a silicon solar cell. There are some relatively efficient examples. Sugarcane in some areas it is rather more efficient, but in most cases, plants have greater concerns in terms of living and fighting off disease and coping with cold weather than converting simply sunlight into biomass, and so their efficiencies are relatively low. But when you look on a molecular scale at the chemistry involved, then the chemistry on the molecular scale of converting sunlight and turning that into chemical bonds, either in the form of NADPH or synthesizing glucose, the efficiencies are much higher, of the same sort of magnitude as a silicon solar cell. And that's, to me, an inspiration that we can indeed, convert sunlight to fuel, to chemicals, with decent efficiencies, and indeed we can use molecular materials to achieve this. From a photochemistry viewpoint, then I've always been interested in the idea that catalysis is slow, but photochemistry typically happens on fast time scales. When you excite a chlorophyll in a plant, the single excited state typically lives for nanoseconds. Whilst if you look at the catalysis of water oxidation by this manganese cluster in the photosystem 2 complex, typically this can run at no faster than milliseconds. And very often, because it has to wait for 4 photons to come along to oxidize 2 molecules of water to 1 molecule of oxygen, it has to wait for seconds to drive this catalysis. So we have to find ways to convert short-lived excitations into long-lived charges which can drive catalysis on milliseconds to seconds timescales. Of course, plants do this by separating the charge. And so they end up with a plus charge on one side of a membrane and negative charge on the other side, and they don't recombine because they're spatially separated. But this costs energy. So around about half the energy absorbed by the biosphere for some is used to drive the electron transfer steps, which separates the charges and gains the lifetime to drive catalysis. I'm going to talk in a minute about this lifetime gain challenge and how it costs energy to gain the lifetime to drive the catalysis. The other inspiration, of course, is pure catalysis. So PS2 is stunning in the sense that it's able to accumulate what are called 4 oxidizing equivalents, essentially positive charges, though they're actually a charge neutral, in a manganese cluster to drive this chemistry of oxidizing water to make the molecular oxygen we breathe and to release 4 electrons, which go on to reduce CO2. It's the primary donor in PS2, P680, is the most oxidizing species in biology because the chemistry of driving water oxidation requires pretty vicious chemistry, not only thermodynamically, but also kinetically. And one of the interesting things here, of course, is that you have to try and accumulate 4 oxidizing equivalents in one place to oxidize 2 molecules of water. Plants achieve this by proton management. So these are proton-coupled electron transfers, where the oxidations are coupled to proton release. So the accumulation of 4 oxidizing equivalents is charge neutral to avoid the Coulomb repulsion. Both of these inspirations are things I'll talk about for the rest of my talk. If we look at the energy cost of lifetime gain, then this is a challenge for many systems. I've seen this is an equivalent picture for a photoanode oxidizing water, actually for a hematite photoanode. The initial excitation is very short-lived, the catalysis is slow, you have to separate the charges, that typically costs you energy. And if you look at the energy cost of lifetime gain, then down here we have PS2, it loses about half a photon energy, around about an electron volt per photon, to gain the lifetime required to drive the catalysis. Metal oxides turn out to have even more severe challenges of a lifetime gain to drive catalysis. Some solar cells do rather better because they're rather good at extracting a charge from a solar cell on timescales far faster than catalysis. But this is the idea. If you want to gain lifetime, it's going to cost you energy. This idea, so this is now switching from concepts to data. What I do is, my group does, is measure kinetics. So on the left, you can see an example of some transit absorption data, which essentially is a measurement of the lifetimes of electrons and holes in various metal oxides. So you photoexcite the oxide in our laser systems. We measure how long these carriers live. This is a log time scale. And you can see that this is a rather short time scale. So this time scale ranges from about a picosecond to a nanosecond. And you can see the decays correspond to the recombination of these electrons and holes. And you can see it's all happening on picosecond or nanosecond timescales. And that's fast, of course. This means that these carriers disappear far too quickly in the essential material to drive catalysis. On the right, you can see some measurements of catalysis. Catalysis is often measured as a turnover frequency, so how quickly the catalyst turns over to drive the catalysis, in this case of water oxidation. And what I've plotted here is some data of a turnover frequency as a function of how many charges are on the surface. I'll come to discussion of these sorts of plots a bit later. The details don't matter for now, but the point is that these turnover frequencies are on timescales of the order of 1 per second. And so we have this huge mismatch in timescale between picoseconds and nanoseconds for how long the carriers live and seconds for the timescale of the catalysis. Addressing this kinetic mismatch costs energy. You can also see that, for example, hematite has really short-lived carriers. They decay in a few picoseconds. Titanium is rather better. The carriers live longer. And the catalysis on hematite is really slow. On titanium, it's faster. Hematite is a rather nice material because it's stable, it's cheap, and it's a good light absorber. But the kinetic challenge means that it's really hard to get hematite to work well as a photocatalyst. Titania works far more easily, but unfortunately titania only absorbs UV light, so whilst the kinetics are great, the colour is not so good. By far the easiest way to gain lifetime is to apply a voltage. This is essentially the idea that if you apply a voltage to an electrode, you can create band bending at the surface. This is a bit of physics, really. Space charge layer. That space charge layer caused by the oxidation of dopants in the metal oxide drives electrons one way and holes the other way and separates charge. And when we do our laser measurements, so we go out to much longer timescales. So this is now timescales of microseconds to seconds. If you don't apply much voltage, there's not much going on. So at a very small potential, then all the carriers still disappear before anything useful. But if you apply a strong potential, you start to see carriers which live for a second because of this bias. And the appearance of these long-lived carriers indeed correlates with when you start to see some current appearing from water oxidation. But of course, applying a voltage is a bit of a disaster because you don't want to have to apply a voltage as well as using the sunlight to drive the chemistry. And so this is it makes the system work, but it's not desirable. And of course, now there are many research studies trying to work out how to gain the lifetime without applying a voltage. And I've just got 3 examples here where you can put a catalyst on the surface, in this case a molecular catalyst. And the further you put it away from the surface, for longer the lifetime, so this is a recombination measurements of recombination, for longer lifetime those charges are on the surface, which can then drive a catalysis. You can put inorganic layers of catalyst on the surface, and again you can gain lifetime because you move the charges to the catalyst and then the carriers are longer lived. Or in this case here, we made a junction between silver and titania. The red is the data for titania alone. You put silver on, and the holes, the charges now live for orders of magnitude more lifetime in order to drive catalysis. And so, in general, this is the story that if you want to drive catalysis of sunlight, you have to design things which can separate charge to drive that catalysis on the right timescales. The rest of my talk is going to be about catalysis. And I'm just going to focus really on one reaction because I find it fascinating, which is how you can oxidize water on an oxide surface. So, and I'm interested in the kinetics. I'm a spectroscopist, so I'm going to be using spectroscopy to try to measure the kinetics of oxidation of water on an oxide surface. And in particular, I'm fascinated by the idea of how we can bring 4 charges together. And typically we're going to talk about surface holes. So typically we're talking about semiconductors, and so a charge on the surface is a surface hole. Very often the hematite is an iron oxide group. But these charges accumulate at the surface and they drive the oxidation of water. How do they achieve that? Are there catalytic sites on the surface? How do these charges come together to drive water oxidation? How do they handle the protons? We saw that in plants, if you want to bring holes together, you have to do something about the charge neutrality. Otherwise, these holes are all going to repel each other and not come together to drive chemistry. Now, when we think about models of the chemistry of an electrochemical reaction, then by far the dominating model of how we understand surface electrochemical reactions is the Butler-Volmer model. So this is the idea that there's typically an activation barrier for a reaction for, in this case, holes oxidizing something in an electrolyte. And as you apply a potential, then the idea is that you reduce the activation barrier for that reaction as you apply a bigger voltage, and the reaction speeds up. And typically it speeds up exponentially because as you apply the voltage, the barrier decreases, and therefore you have some sort of Arrhenius type behavior. And you can see typical examples here of plots of a voltage versus the current for many different electrocatalysts. And you can see typically indeed that the reaction speeds up approximately exponentially with applied voltage. This model is widely used to explain many metallic electrodes, in particular for water oxidation and many other reactions in electrochemistry. The idea essentially here is that if you want to think about it in terms of rate constants, as you apply a potential, the rate constant gets faster because you apply, it should be a rate constant increasing, with increasing over potential because you make the barrier smaller. Now, I've struggled to understand how that sort of model can work in the sort of metal oxide electrodes which I was interested in. And I've been much more interested in the concept of how, as you accumulate more charge, more oxidizing equivalents, then those charges can come together to drive a chemical reaction. And for example, if you think about a semiconductor, then typically if you apply a potential to a semiconductor, then you accumulate more charges at your valence band edge, which can then increase the rate of reaction, not because you change the barrier to the reaction, but because you have more species present to drive the chemistry. The same can happen if you shine light on your semiconductor. Again, you generate more charges, which can accelerate the reaction. This sort of model is better understood not in terms of Butler-Volmer behavior, but in terms of a rate law. It's the idea that the rate of water oxidation accelerates as with some rate constant and some dependence upon the density of charges on the surface. Whilst it's a relatively a simple model, and indeed has been proposed many, many years ago, it's been very rarely applied to try to understand the electrocatalysis or the photoelectric catalysis on some of the materials now of interest for solar-driven or indeed dark water oxidation. And so we've been interested in trying to understand whether this sort of model might help us understand some of the reactions on some of the materials we're interested in. And we were particularly interested in using spectroscopy to help interrogate the system. And so essentially the idea here is that we wanted to be able to measure this accumulation of charge, or this accumulation of oxidizing equivalents in our metal oxides during the water oxidation. And it turns out, for example, that for many metal oxides, if you increase the oxidation of that oxide, you see optical changes. And this is, for example, for a nickel oxyhydroxide electrocatalyst. If you oxidize it, then it becomes colored. And you can see the appearance of an absorption band, indivisible. If you know the extinction coefficient of those charges, then you can turn that optical signal into a plot of charge density, and then you can plot that charge density or that hole density versus your current, and that allows you to do a rate law. You have a measurement of the flux of oxidation, you have a measurement of the density of oxidizing species from your optical signal, and then you can do a rate law analysis, and we did this for nickel oxide, and we found that the water oxidation was fourth power in the density of nickel 4+ species on the surface. You get really weird units for your rate constant because it's a fourth order surface reaction, so ignore that funny unit. But the idea is that we can apply the concept of a rate law to measuring kinetics on a surface. We could do the same thing optically for a light-driven reaction. In this case, we change the density of charges on the surface by changing the light intensity. We can measure the density of charges at the surface from an optical signal. We can measure the current by a simple current measurement. We can plot one against the other, and we can get a measurement of the current versus the density of charge on the surface. In this case, we found, this is for hematite, and we found that at a low light fluxes, the reaction was first order, so you double the amount of charge and the rate goes up, the current doubles. But at higher hole densities, 1 sun is around about here, and so these are at 1 sun irradiation. If you double the density of charges at the surface, the rate goes up by a factor of 8. And that we found quite interesting. Now, this idea of rate law analysis is somewhat controversial, but we found it to be quite useful for a whole range of reactions. So we've looked, for example, at proton reduction on ruthenium oxide, and we find it was second order in the second reduction of ruthenium oxide, and we attributed that to homolytic reaction path. We looked at methanol oxidation on hematite. We found this was second order in the density of holes at the surface, and we could suggest a particular reaction mechanism associated with that rate law. We've already talked about the fourth order behavior on this nickel iron oxyhydroxide. I'll come back to that a little bit more at the end. But maybe most controversially, we've looked at this hematite and now other photoanodes and observed third order behavior. Whether a Butler-Volmer or a population model is more appropriate is rather controversial. We've done a lot of work trying to understand whether this population model makes sense. And so, for example, you can see measurements here of where we've done rate law analyses for different reactions and different applied potentials. And so the idea here is we are changing the electrostatics of the interface, and we find it makes essentially no difference to the kinetics as long as we measure the kinetics per surface hole. So you can see here, for example, measurements of the density of holes at the surface and the measurement of the rate constant. And the rate constant is independent of surface hole density and indeed applied potential. These sorts of pictures suggest to us that indeed a population model, a rate law analysis, makes rather more sense than a Butler-Volmer analysis for many of these systems. Because we're measuring rate constants, it makes it rather easy to measure activation energies by doing Arrhenius analyses. So if this was an Arrhenius analysis of water oxidation on a hematite surface, and what we observed was that the first order reaction was activated at around about 300 millivolts or 7 kilocalories per mole activation energy, but the third order reaction was almost activationless. In other words, if you increase the hole density on this hematite surface to around 1 hole per square nanometer, which corresponds to pretty much nearest neighbor oxidations, then you start to oxidize water by a reaction path which is almost has no activation barrier, which suggests, of course, that hematite is able to access a reaction path where essentially it acts as a catalyst to lower that activation barrier. Now, you can start to think about mechanisms when you start to measure rate laws. I mean, we haven't just measured the rate law. We've measured, for example, the rate constant as a function of temperature to get to the activation energy, a function of pH, and as a function of hydrogen deuterium exchange. And we then went to the sort of the modelers who haven't been trying to understand how metal oxides work, but have been trying to understand how PS2 oxidizes water. And they applied the sort of molecular picture of water oxidation which they developed for photosystem 2 to the hematite surface, and came up with at least a suggestion of how hematite can oxidize water, where essentially you generate 3 oxidations, but each oxidation is charge neutral because you have the same sort of proton release which we have in photosystem 2, which allows those holes to come together to form a complex where the OO bond formation is the rate determining step, and that OO bond formation requires 3 holes. That's a rather complicated model. This is essentially the idea that you generate 3 charges, 3 surface holes on the surface of hematite. They come together, they access the rate determining step of OO bond formation, and then you have a final hole which generates the release of the oxygen. We find, whilst this is not a definitive model, we are at least finding that these sort of rate law analyses are giving us some insight into catalytic mechanism. I'll just finish by an example of looking at in a little more detail at the electric catalysis, in this case of nickel oxyhydroxide electric catalysts, where we are varying a small amount of doping by a secondary metal, in this case a range of metals, manganese, cobalt, iron and zinc. And our colleagues in Spain observed that iron was the best, and when we changed to other metal dopants, the electric catalyst works rather less well. And we were interested in trying to understand why that might be. We measured how easy it was to oxidize these different electric catalysts by measuring the density of oxidized species on the electric catalyst by our optical measurements, our spectroscopy, versus voltage. And we observed that it was rather easy to oxidize the manganese and cobalt, and rather hard to oxidize the zinc or the undoped. And indeed, of course, these are the species which go on to drive the catalysis. We could then measure how quickly those oxidized species drive the catalysis, and we found that iron was the fastest at driving the catalysis, whilst the zinc and the manganese were rather slower. How we understand this allows us to draw a rather simple picture of why these different systems show faster or show better electric catalysis than others. And so essentially we find that the manganese and the cobalt are rather good at oxidizing the water, but are not good enough at oxidizing the water because the oxidized species there are not oxidized enough. The zinc and the undoped are too hard to oxidize. Their kinetics are reasonably fast, so their turnover frequency as a function of potential, it can be fast enough, but it's too hard to oxidize them. They're too hard to oxidize, and so you can't generate enough species to drive a fast reaction. The iron is a sensible compromise between this potential determining step and the rate determining step, and gives the highest performance. I'm aware I'm pretty much out of time now, so I'm going to finish by, I hope, giving you a summary of what I hope I've been talking about and I hope you found interesting. It's the idea that synthesizing fuels with sunlight, I think, has the potential to be part of our story of how we move away from our dependence upon fossil fuels. Chemistry is the key here, and a wide range of materials and device configurations which we're thinking about. If we think about light-driven reactions, but I personally find the challenge of lifetime gain to be really key. How we can gain the lifetime required to drive catalysis. When you think about the mechanisms of catalysis, then we're finding that using operando spectral electrochemistry allows us to measure the accumulation of charges of oxidized equivalents on an oxide surface. And that allows us to understand how the kinetics of, in this case, water oxidation depends upon that charge accumulation. And we find that interesting. And we find, at least at the moment, that the results we get suggest that very often it's more appropriate to think about kinetics in terms of rate law analyses rather than in Butler-Volmer type pictures. I, of course, must thank everyone who's been involved in the work I talked about today. I particularly, of course, my research group, and I showed various faces of various people who've been involved in the research I talked about during my talk. Of course, we have many wonderful partners from around the world who we work with in terms of material synthesis, in terms of modeling, and in terms of some other aspects of analysis. The funding, of course, is critical and very often becoming increasingly challenging. I'll leave you with my summary. I hope that was interesting. And with that, I'll finish.
Bob, switch on your microphone, please.
I don't think we can hear you yet.
Yeah. Bob, switch on your microphone.
Yeah, you'd unmuted me, mate. Okay, fine. Yes. So before we start, first of all, thank you very much for that very interesting talk, James. And we can now open the session for questions. Do we have anyone who immediately wishes to pose it, ask a question? Otherwise, I may use the chairman's prerogative and move in. Let me just ask you, you talked about a lot of metal oxides and various ways of catalyzing water oxidation. I was interested to see that at the end you had included cobalt. A lot of biochemistry seems to be going into looking at cobalt as a potential catalyst for water oxidation. What's your thoughts on the potential role of copper in this, of cobalt in this kind of chemistry?
So there's a lot of interest in cobalt oxide as an electrocatalyst for water oxidation, and Dan Nessera particularly has been getting very excited about cobalt phosphate derived cobalt oxide as a water oxidation catalyst, and it is very effective. And so I think if I go back, I actually had an example of a cobalt oxide here. Yes.
Yeah.
Can you still see that?
Yep.
So this is an example where the cobalt oxide was indeed helping to separate the charges on a hematite surface. But the cobalt oxide itself, it turns out, has really slow oxidation kinetics. It's an electrocatalyst in the sense it can drive water oxidation at a rather modest overpotential. But a cobalt oxide electrocatalyst only works because typically they're permeable to water, and so they have a huge internal surface area to drive the reaction. If you measure the kinetics of water oxidation from those oxidizing species in the cobalt, they're typically on the timescales of hundreds of seconds. So orders of magnitude slower than hematite oxidizes water. If that doesn't mean to say it's not a good electrocatalyst, it is, because it oxidizes a lower overpotential and it can have a high surface area. But so, for example, in the case here where we put cobalt oxide on the surface of hematite, everyone thought the cobalt oxide was helping because it was catalyzing water oxidation. It turned out, actually, in this case, when we added the copy to the hematite, it enhanced the performance because it formed what we call a Shockley junction. Most of the oxidation was still coming from the hematite. The cobalt was actually there to increase the band bending in the hematite, which actually rather surprised us and surprised a lot of people. So in that case, it's about kinetics, that compared to the nickel oxyhydroxide or the iron oxyhydroxide systems, the systems being measured with cobalt are catalytically slow.
Yeah. Okay, thank you very much. Do we have other questions?
Yes, a question from Bo.
Bo?
Yes, I'm here. Yes, you have talked a lot about different metal surfaces, but how are these surfaces comparing in terms of efficiency compared to plants using chlorophyll? And where do we stand today in respect of chlorophyll and synthetic chlorophyll to use the sunlight to convert into carbon, hydrogens, and hydrogen?
That's quite a big question to answer.
That could be the subject of another lecture.
I also work a lot on molecular systems. I haven't talked about those today for oxidizing water. If you focus on the level of the rate constants or the turnover frequencies for catalysis, then PS2 has a turnover frequency of about 1,000 at best. So for manganese cluster. Some of the inorganic electrocatalysts are able to work at somewhat similar overpotentials. Similarly, some of the molecular catalysts people are starting to synthesize can work at similar overpotentials. PS2 is particularly good that it can work at a very low overpotential, which of course is critical. So it's able to harness oxidized chlorophylls to drive the chemistry without them being too oxidized in themselves. If you want to think about, can you go to a molecular-based system for doing the whole thing, for absorbing the light and driving the chemistry, then there's a huge amount of research of people who are synthesizing molecular light absorbers and coupling those to molecular catalysts to drive the chemistry. So far, I would say that all molecular systems are proving pretty challenging to put together. for most of the systems which are molecular systems to drive the chemistry are in suspension, where you have molecular light absorbers diffusing around in a liquid, which then bump into catalysts and drive that reaction. Some of those work quite well, and some of their efficiencies are reasonably good. So far, systems which have at least some element of a solid inorganic material are looking more promising. I'm not sure I'd answered your question, but hopefully answers a bit.
Thank you.
Bob, a question from David.
Has any work been done on tungsten oxides? Because I believe these are quite good semiconductors.
Yes. Again, I'm not sure you can see. Can you see this slide?
Yes.
So, tungsten oxide is indeed a very interesting material as a photoanode, particularly because it's acid stable. Right. So it can oxidize water in the presence of lots of protons. And when we've measured for kinetics of water oxidation on a tungsten oxide surface, it's an order of magnitude faster than these other oxides. So I think it is a rather good catalyst for water oxidation when you measure it in terms of a turnover frequency. So certainly it's a very interesting material and something which we are doing quite a lot of work on. The problem with tungsten oxide is that it tends to be highly defective. It's very easy to generate oxygen vacancies in tungsten oxide, and this means that it's typically a very strongly doped material, and those defects, trying to get those defect densities right, is quite challenging to get the best performance.
Okay, thank you very much.
I can see a question from Rachel.
Yes, Rachel, please.
Hello. So in your presentation, you actually mentioned an idea about green hydrogen from water and solar energy. So I'm just a junior in chemistry, so I just wanted to know, how did you develop that idea? How did you come up with the idea?
Oh, I didn't come up with the idea. Jules Verne did 150 years ago. This is the idea that, of course, there's a lot of interest now in hydrogen as a fuel. And we even now have hydrogen-powered buses going around London. But almost all the hydrogen which is currently used comes from methane. And so people split methane to, and of course the process of synthesizing the hydrogen releases CO2. And so whilst those hydrogen-powered buses appear wonderful because the only stuff coming out of the tailpipe is water, the overall, they are not helping, or they don't contribute to the global reduction of CO2 emission. And so we need to think about pathways to make hydrogen which are carbon neutral. And green hydrogen is the concept of making hydrogen from water using renewable power.
Thank you.
Does that make sense? Which is essentially what I was talking about. Of course, currently making hydrogen using renewable power, such as from sunlight, is currently too expensive, which is why we need to try to find cheaper catalysts and cheaper materials and all the things I was talking about today.
Okay, Tim, please.
Yeah, I'm just wondering. We see lots of developments currently with people using, let's say, off-peak wind power to electrolyze water to get hydrogen,
sure,
and then combining it with carbon dioxide to produce methane or fuel.
Yep.
I was wondering how what you're doing is going to fit in or supplant that. I mean, is it going to fit into that process? Is it compete, or is it actually something completely different?
Well, I'm a scientist, not an engineer, and so all we're doing is looking at some of the function of some of the materials which may go into future examples of that technology. So, for example, currently electrolyzers are relatively expensive, and the catalysts in those electrolyzers are typically based on rare earth metals. So platinum and iridium and all this. There's a huge amount of interest in trying to find cheaper catalysts. And so one of those cheaper catalysts is, I should have said earlier, I'm sorry, is these nickel-ion systems, which are potentially far cheaper than iridium oxide as a catalyst for water oxidation, but currently are not stable or efficient enough to be a useful alternative. And so it's very interesting to try to at least understand how they work and then think about how we can make them better. We don't make them better, our colleagues do. We just try to understand how they work.
Thank you very much. Do we have any other questions?
No.
No? Well, then let me take this opportunity once again of thanking James for a very interesting presentation, and thank you for your participation. I'd like to take this opportunity to welcome to our midst not only members and friends of the Royal Society of Chemistry Belgium section, but also some friends from the Flemish Chemical Society here in Belgium, who were also invited to take part. To all of you, thank you very much for your participation. Thank you, James, for your help and contribution. And I hope you've enjoyed the little appreciation of our thanks, which you, I'm glad to hear, received already before the talk.
Indeed. Thank you very much.
And to all of our people watching and joining us, I remind you of our next talk, which will be our next meeting, which will be on the 14th of March. Thank you very much, and have a very good evening. Keep safe. We look forward to seeing you again soon.
Thank you very much.
Thank you.
Thank you.